Thanks for joining me to listen to the lecture regarding chapter 2.5 of hydrogen bonding. So we are now almost done with the different bonding types, and now we will go through with the special case of a hydrogen bonding. And this is really neat from the point of view that this is not a very important bonding type in terms of physics, but this is especially important when we are thinking of chemistry and biology. So when we are thinking of chemistry and biological structures, it is the hydrogen bond that rules. And of course the van der Waals forces, but these kind of later forces we're treating, like these really rule when we go to these more complicated soft matter structures. So let's get forward. We have 2 slides on the way. So I will start by just saying that the cohesive energies that we are dealing with here when we're treating hydrogen bonding, they are quite a bit weaker now than the ionic or covalent or metallic bonds. So like I said, these are not the strongest of bonding forces anymore when we have hydrogen bonding taking place, but nevertheless, this is way stronger than the van der Waals forces we will be dealing in the end. So instead of energies, we're speaking of around 100 millielectron volts per atom, and this is different than the roughly 1 electron volt per atom when we're speaking of ionic, covalent, and metallic bonds. So the bonding strength is a different order of magnitude, and maybe this also helps us to understand that why water ice starts melting at around 100 degrees of Celsius, where, for example, diamond doesn't start melting until 1600 Kelvin Celsius has been reached, or something like that. Or silicon nitride starts melting only after 2000 Kelvin, or silicon carbide, if I recall, after 2500 Kelvin or something. So once we understand these bonding energies, we can also estimate these kind of properties. What are, for example, the melting points of different solids. So while hydrogen bonds, they don't form very, very solid structures and rigid structures, they are very important when we are dealing with more complicated structures, especially in biology. So for example, when we're looking at the double helix of a DNA molecule, that's where these forces play a role. When we're looking at the fibril collagen proteins, and that's a very abundant protein family in mammalian tissues. So the different collagen proteins, they're also being glued together in these specific structures because of hydrogen bonds. Water ice, that's a classic example we see in everyday lives, either by putting our heads into the freezer, or by walking outside in Scandinavia in the wintertime. I have a project. I would want to grow up a monocrystalline water ice, but it turns out that it's not as easy as one could imagine. I managed with other solids like copper sulfate, alumina, these other materials can be relatively easily grown into monocrystalline solids, but water ice, that's next on my pipeline. Let's see if I can manage somehow. Maybe I should resort to kind of zone melting or other approaches that are being used to purify the crystalline structures in semiconductor industry when one would want to make pure water structures, because the usual ice that we have, it's a very rough, coarse polycrystalline material, and it doesn't look very nice and transparent. So I would love to have these kind of more beautiful ice cubes in the next dinner party we have. I don't know. So let's consider H2 molecules in water. And this is a schematic that is illustrating what's happening. So we have one oxygen surrounded by 2 hydrogens. And this, we know that the water is a polar liquid, so that there will be a electronegative oxygen atom. And because of that, this the electron orbitals will be shifting. So we have hydrogen parts, and they are electropositive, so they like to give out 1 electron, and the oxygen that wants to receive electrons. And what happens then is that the charges get shifted slightly, and this gives rise to intermolecular electrostatic forces. So I'm trying to show them here with the green here. So we have a little bit more of a negative charge here, and it's not an integer of a charge, so that's why delta minus. And in here we have slightly positive charge, and it's not a integer of elementary charge, so that's why delta plus. And then this green Coulombic attraction here between is our hydrogen bond. And this is what happens in the case of hydrogen molecules, and this is also what happens when we have hydrogen and oxygen in other materials. And we do have plenty of that in different organic molecules. And this is the what I had to say regarding hydrogen bonding, and I will just recap by saying that it's not the strongest, but in system, when it plays a role, it really plays a role. And hopefully, like you remember water ice, and the fact that water ice melts relatively easily compared to other solids that we can imagine, so that that provides us a kind of semi-useful rule of thumb that the bonding energies are not as high as with covalent, ionic, or metallic bonds. So I rest my case here, and thanks for listening. Bye-bye.